Good afternoon, everybody. I'm Jun Yan from statistics at UConn. This is the third time my class presenting at the New York Open Data Week. And in the last 2 years, we did the crash data, the 311 request data. And this year, we are looking at zooming in to rodent sightings and rodent inspections in New York City. And this was a homework midterm project, and it's a midterm project where the professor doesn't have the answers. Our class has collectively developed our notes. If you go to the event page at end here, this is our the class notes that I and my students are developing. This showcase will demonstrate what the students learned, the whole cycle of a data science project, from data preparation, exploratory data analysis, analytics, to visualization. Without further ado, I will give the stage to my students. Vincent, you will be on.
Hello, everyone. My name is Vincent. Today I'll be doing my project or presenting my project on data cleaning for the rodent inspection data. A quick introduction. I am a statistics major with a minor in computer science. I'm a senior, hopefully graduating in 2 months, and I'm from Danbury, Connecticut, which isn't too far from New York. A quick overview. I want to investigate the rodent problem using the 2022-2023 data for rodent inspections, primarily focusing on initial inspections and compliance inspections. Necessary first step for data cleaning will be analyzing if there's redundant data, if there's missing data, or if there's any invalid data. I then proceed by filling in the columns that are important to the investigation, and I will also discuss the cleanliness of our data. From the user guide or the data dictionary, we have some columns here, starting with inspection type. Again, it will be initial or compliance. We have work order ID, which is unique for every inspection. We have job ID, job progress. I mainly want to highlight BBL, which is a burrow block and lot code, which will help me identify certain aspects from the column. This also is the burrow code and uses the block and lot number. We also have house number, street name with zip code, and we have the X and Y coordinates using the New York State Plain Long Island coordinate system. And we also have the longitude and latitude and burrow result and the approved date. To start, we have all of these columns in the CSV file when it is downloaded. What we do notice is that we have additional column names that are not present in the data dictionary. And for each entry, it uses 30 columns per row, and we have roughly 407,000 rows. And I did some extra digging and found that 80% of these are initial inspections. I analyzed how many were missing. We see that we have the count of how many entries are missing per column. So for mostly blanks, which is over 75%, we have the X and Y coordinates at roughly 80%. We have a few blanks from 1 to 10%, which are all the column names below. I mainly want to highlight zip codes because there's another column called zip_code. So there's a little conflict there. And then we have columns where nearly none, so it's less than 1%. We have zip code, house number, street name, result, and burrow. Now, going back to zip codes, we have two columns that indicate a zip code, but one of them is incorrect. We notice from this image, on the right side, we have zip codes such as 17212 and 17213. I think this will be 212, which is Huntington County, Pennsylvania. But as we know, valid zip codes in New York only range from 10,001 to 11,697. It's also noted that there's 7.6% of the entries that are missing in the zip codes column. And it makes me wonder, like, what is the purpose of that column? It could be based on the owner of that specific tax lot. We used another data set. It's primary land use tax lot output, and that data set had a lot of common columns that I was able to use to fill in empty cells. Specifically BBL, which is borough code, block, and lot, and the X and Y coordinates and the longitude and latitude. You'll see that we have 326,000 entries missing. And after filling them in, you will see like the before and after. Even with the BBL, I was able to create all the BBLs so I can use it in the Pluto data set to find the exact entry. And with the house number and street name, once we filled in the latitude and longitude, I was able to reverse geocode to find the missing values. And you see how there's some that are empty. With the reverse geocoding, I was able to find some of the empty cells. Although we should note that some of the entries are not specific tax lots. It's representing an entire street, such as East 161 Street and Woody Crest Avenue. So it's hard to find a specific latitude longitude if we're indicating the entire street. And with zip code, I was also able to use the BBL and the postcode from Pluto to fill in the missing data. And we see that from the initial count of missing data, once we filled it in, it got significantly reduced. And we have the numbers here. There are some inconsistencies that I saw within the data. Going back, we have 21 results that were missing. Those are definitely harder to fill in because from me, I do not know the actual result from that inspection. Boroughs, we do have 3 that were missing. These could be filled in manually just by looking at the address, a house number and street name provided. We do have borough code, an inconsistency with borough code, as with the entry of 9, we have 3 of them. It could represent that as missing, but the only valid borough codes are from 1 to 5. There's also an invalid block number, which is supposed to be 5 digits, but we have one entry that is 6. And when comparing the data to Pluto, one of them is 670 Lafayette Street in Brooklyn, and from Pluto, it comes up as Tompkins Avenue. This can be a little confusing just because one is more specific than the other, such as where Tompkins Avenue is the street to the right of the park. We also have invalid entries such as the borough code, the invalid block number. Once I filled in the zip code, I found that we still had 117 invalid zip codes from the list of acceptable zip codes. And this can definitely be investigated further to analyze what was wrong with the inspection data. And how can we improve this data set? We want to remove redundant and insignificant columns. Redundant columns would include location, as we already have latitude and longitude, zip codes, because this one is invalid and does not affect our investigation. We want to remove borough code, block, and lot because we already have the BBL numbers. And insignificant columns, we have borough boundaries, community districts, city council districts, the building identification number, and the neighborhood tabulation area. And there are some other columns that I was able to fill, but they can also be removed, which would be police precincts, the community board, council district, and the census tract. We could also specify the range of values for columns that take integers, so it's a little more clear, such as can the block and lot start as 0 for a value? And we can also fix the small errors in regards to result and borough. And we can also be more specific on the inspection locations, such as the park before whereas it would be a little confusing with like two different streets. And that is all for my presentation today.
Thank you, Vincent. I think we can move on to the next. Pratham.
My name is Pratham Patel, and I'm going to be exploring the data set that Vincent has just cleaned for us. So a quick introduction about myself is I am a senior here at UConn, hoping to graduate in May, with a bachelor's degree of science in mathematics, statistics, and a minor in computer science. I'm from Manchester, Connecticut, and the main reason I decided to take this course was to learn more about the data science workflow and various techniques, and to familiarize myself with a lot more programming packages on the way. So the main goal for this data exploration is to work with our data to see what kinds of trends, basically to explore what our data looks like and how interconnected it is with the rest of it. So the first thing we'd like to do is work with the result column in the data set, which typically has various labels from passing to not, and oftentimes giving a reason why. What we decided to do here is create a secondary column called passing, which simply passes a yes or no as to whether it passed the inspection that was run. This will allow us to really see how often these inspections pass and how often they fail, and as well as interlink them with various other columns, various other data points in the data set. So we want to test how all of these variables can predict whether an inspection will pass or not, based on everything else from location to the type of inspection and various other things. So the first thing we want to see is if the type of inspection influences the passing rate. And for the data set we have, there are two kinds: initial, which is usually in response to any kind of 311 or general complaint that is sent out, and compliance, which is generally a follow-up to those initial, in the case those initial tests fail. In order to see if these different types are significantly different in passing rate, we're going to run a hypothesis test, which will see if there is a significant difference between the passing rate of initial inspections and compliance tests. So I have a simple table, right? I have made a simple table right here, which divides the entire data set into compliance and initial, and shows where the tests had failed, or how many tests had failed in proportion to the amount of tests that passed. And the main method I use to test these is via a non-parametric, since while trying to test them with actual parameters would be sufficient, it would be hard to prove the various assumptions that are needed for that. So I opted for specifically the Mann-Whitney U-test, which I will jump ahead real quick. It's a Mann-Whitney U-test, otherwise known as the Wilcoxon rank sum test. And the short of it is that it takes all of the data that we have. In my case, I used various proportions from samples of the data and ranks them accordingly. And the way this is tested is it compares the distributions of those proportions and sees if the compliance tests, their distribution of those varies significantly from the initial. Basically, we're looking to see if the curves are significantly different in any particular way. So we are looking to see if they are different in any way. So using the data and sampling it repeatedly, I was able to run this Mann-Whitney U test and find that here, this p-value is very, very small. This e to the negative 34 indicates that it is a very, very small decimal, which is good for us because the lower the p-value is, less likely it is that the null hypothesis is likely to be true, which means that they are significantly different in these different tests are significantly different, which, while it is obvious from the proportions we see here, oftentimes the data sometimes is too close to tell, which is why we need these hypothesis tests to see how significantly different they are. In our case, it is very. Another statistic we wanted to look at was location. Does the location in New York influence how often these tests pass or fail? So again, here is a table with all of them. And while most of the boroughs hover around the 70% passing mark, we see that Queens is significantly less passing, regardless of inspection type. So again, we have another hypothesis test to see if they're all the same distribution or if two or more are distributed differently. I have a graph here with the same proportions in a sort of bar chart format, this time divided by inspection tests. So we can see that, as we saw with our first test, the compliance tests are generally have a much lower passing rate than the initial tests. And again, we see that in this graph, Queens is a significantly lower passing rate than the others. So the assumptions we take for this one is that the first two are actually the exact same as the Mann-Whitney U test, which is that they're independent and ordinal, which means every single test should be different from one another, and these samples that I'm taking, those proportions, are ordered when when the test is being run. And specifically for multiple categories, each sample has to have at least 5 observations. With how large our data set is, this should not be a great worry. So for a test like this, we are going to use the Kruskal-Wallis H test, which, as I showed before, it checks for differences. If there's at least 2 boroughs in our case that are significantly different in passing rate, and for both initial and compliance inspections, the p-value is significantly smaller than our previous tests, which indicates to us that that the boroughs in some way are different, and especially with how much lower the Queens passing rate is, we can definitely see that Queens is probably the outlier we want to take a look into. And the last test that we wanted to see is if time of day influences it at all. I have two more visualizations here with the bar graphs, each divided by borough and by inspection type to see, excuse me, and then split up the 2 different sets of graphs by time of day. So across the 2, it's hard to say. All of the graphs seem fairly similar between the 2 times, with the somewhat exception being Queens, where it seems a lot more even in the afternoons. We will again use the Mann-Whitney U test here, since it is simply comparing morning and afternoon. And while it is significantly larger, see how it's only 3 decimal places from, 3 decimal places, or sorry, the p-value is only in the thousandths place. It is still significantly smaller than any significance value that we would try to test for. So as a result, we can reject the null hypothesis and say that these distributions are different, and that there is some credibility to saying that these that passing rate in the morning for inspections is significantly different than in the afternoon. So the grand point of most of these inspections is, if there is significant difference, that is certainly something to be looking into whenever we're trying to find some sort of causality for a lot of these inspections and sightings, especially in the case of having the tests pass or fail. Right, and as I said before, like Queens has across the board much, at the very least, different passing rates than the rest of the boroughs. So looking into other factors such as like what kind of climate there is in the borough and whatnot is certainly worth inspection. I believe that's all I have.
Thank you, Pratham. I think Isabel, you can go and we can answer the questions at the end. Yeah.
So my presentation is performing some data analytics on the same data set that both Vincent and Pratham worked on. So a little bit about me. I'm also a mathematics statistics major with a computer science minor here at UConn. I'm a junior and I am currently interested in sports statistics and sports analytics. In baseball, I work for the UConn baseball analytics team. And my personal goal is to learn how data science can be used in sports analytics to improve team and player performance. So the first thing I did when looking at this data set was aggregating the inspections by zip code so we can see how the passing data differs by location. So I created a new data frame and added a few features to go with it. So the 4 features I added were an initial, which was just a count of the number of initial inspections by zip code. N init pass only counted the passing initial inspections. And then I added N compliance and N compliance passing, which do the same thing, but just for the compliance inspections. I also filled null values with zeros, as you can see here, because this data set is a count, so we can use zeros. And then I also merged it with the New York City 311 call data and added a column that contains the number of rodent sightings in each per location for each zip code. And so you can see down here with the N compliance and the N initial, there are going to be a lot of zero values because, as Pratham said before, or Vincent might have said that only about 80% of the inspections were initial. So there are going to be a lot of zeros for where there aren't compliance inspections, where there aren't initial inspections. The next thing I did was used zip code to find demographic data. So there is a package called US zip code that allows you to search by zip code and provides a list of demographic and socioeconomic variables for that area. So the ones I added were population and population density, housing units and occupied housing units, median home value, and median household income. So the population density is by square mile. And we can also see that the housing units and occupied housing units are going to be fairly similar since most housing units in an area will be occupied. And then, of course, as expected, the median home value is going to be in the hundreds of thousands and the median household income in the tens to hundreds of thousands. So using this newly created data frame, we want to use a binomial regression model to predict the probability of an initial inspection passing. in order to do this, we need to create 2 sub data frames. And so the first one will be our X, which will contain all of our predictors that I just spoke about. And the Y will contain 2 columns and will be the probabilities to be predicted. So I have here listed the predictors, which I went over. And the Y is going to contain N initial pass, which is the past inspections, and N initial fail, which I found by just subtracting the past inspections from the total number of initial inspections. And so when running the regression model, it will calculate the probabilities based on this this binary variable. So before actually fitting the model, I made a few adjustments. The first thing was to scale predictors just so when I get my output, it's easier to interpret. So the population density, housing units, and occupied housing units were divided by 1,000 because this is usually the terms in which you would speak of these variables. And then median home value and median household income divided by 100,000 because, again, these values will be in the hundreds of thousands. Then I removed rows with 0 initial inspections to allow the model to converge better. And because we do not need the, since we're only working with initial inspections in this case, we don't need any rows which have 0. And then I centered the data for each column by subtracting the mean of that column. And so here on the right is the code I used to fit the model. So I used the stats model package and specified the family as binomial so that the program will know to output probabilities. And then I fit it. So here's what the entire output summary looks like, but we're just going to focus on a few parts, which are the coefficients on the bottom, and then in the top right, the deviance, the log likelihood, the deviance, and the Pearson chi-squared, which are our goodness of fit measures. So interpreting the coefficients, we're going to have 2 main categories. So we have our positive coefficients, which are the sightings, population, occupied housing units, and median household income. So these make sense if we think about, for example, median household income. As the median household income goes up, we're probably looking at a wealthier neighborhood, which might have better services to reduce the or to increase the cleanliness. So for each increase of 1 unit, which for median household income, we're talking about hundreds of thousands, there will be some amount of increase in the log odds of the initial inspection passing. So if we look back at our coefficients, we can take an example for if we look at population. So for population, we're looking at thousands. So for it, in each increase in 1,000 people, our log probability will increase by 0.0111. Then we have our negative coefficients, which are population density and housing units. Again, for example, this makes sense because in increased population density, probably going to be a little less clean, a little less well managed, and it'll make it more difficult for inspections to pass. And again, this is similar in that for each increase of 1 unit, instead of the log odds of initial inspections passing increases, it will decrease because these coefficients are negative. Then to analyze our goodness of fit, so we're going to look at these 3 measurements. So the deviance and the chi-squared are fairly similar. They both are going to measure the fit of the model by comparing the statistic to a chi-squared distribution. And then the log likelihood also measures the fit with a larger value being better. So if we immediately look at our log likelihood, we have, it's around negative 200,000. So clearly that isn't what we want. We would want something a lot higher. And then for a deviance and chi-squared, we need to perform another test where we compare these statistics to a chi-squared distribution with 140 degrees of freedom. And this degrees of freedom comes from subtracting the number of predictors from the number of observations. So we have, and subtracting 1 from that. So we have 140 observations minus 7 predictors minus 1. So for the deviance, I used R to to calculate the probability for the chi-squared model with 140 degrees of freedom. And then because we want the lower side, I subtracted from 1. And this actually rounded down to 0, whereas we want it to be closer to 1. So this suggests there were very large residuals and further suggests there was a lack of fit. Then for the chi-squared statistic, this is actually a hypothesis test where the null hypothesis suggests that the model fits, and the alternative is that the model does not fit the data well. So again, I want to find the lower probability of this 324,000 is the chi-squared statistic given, and with our degrees of freedom of 140. And this again rounded down to 0. So we can reject the null hypothesis and conclude that the model does not fit as well as we would have wanted it to. So some possible issues that could have occurred. There's definitely a major issue of multicollinearity. So population and population density, of course, will be very much related. And as we saw earlier, the housing units and occupied housing units are very similar in terms of the actual values in the data set. So the fact that these are so closely related could have caused some issues with the model. We also only used 7 predictors, which in this case may not have been sufficient to for the predictions. So if I were to have more time and work on this further, I would probably look at some other demographic variables that might have had more of an impact on the model. So in trying to fix these issues, again, reduce the issues of multicollinearity by maybe dropping columns, trying to find which columns are best to keep, increasing the number of predictors, and finding what predictors are the most significant in order to just use those that have that explain a lot of the variance of the model. And that is it for me.
Thank you, Isabel. Our last presenter is Josh Lee.
My name is Josh, and I will be presenting on the final kind of portion of this presentation, which is answering the question from more of a spatial and visual perspective of where exactly is the rodent problem most significant in New York. So just a quick little introduction about me. I'm an undergraduate student studying statistical data science at the University of Connecticut, and I'm really passionate about extracting insights from data, building models, and communicating research results like I am right now. So the way this presentation is going to go is we're going to talk about where the rodent problem is most significant in New York. But this question might not be it might seem obvious, but there are a couple of ways to approach answering this question. Specifically, as was mentioned in previous portions, we also analyzed the rodent sighting data in addition to the rodent inspections data. And these data may or may not overlap. We will address that in a few moments. Additionally, we have the compliance inspection data on top of the initial inspection data to kind of extract an understanding of where the rodent problem is most significant. So to start with, we're going to take a look at the rodent sightings. Now, how do we measure this? Of course, the natural way to look at it is just where are the rodent sightings occurring from a spatial perspective. And to kind of present this, I've plotted several graphs of the rodent sightings data across New York by zip code level. And as you can see from the graphs, there are 2 main points. So in the top level graph, we show the unscaled sightings of rodents by zip code. And you can see these 2 kind of standout areas. The first area is in the northern part of Manhattan, where we see around 2,500 rodent sightings in the data. Those occur over a very select number of zip codes. And this tiny portion, this little L-shaped corner of Manhattan will continue to show up again and again throughout the presentation. Additionally, we can take a look at this from a log scale perspective in the second plot, which just provides a more gradual, even gradient for understanding how rodent sightings are distributed. But again, this tells the same story, which is that there are these two areas in northern Brooklyn as well as northern Manhattan where rodent sightings are occurring at a much greater rate. But we can also compare this to the inspection failures. So we would expect that given these rodent sightings, these areas will also experience rodent inspection failures at a higher rate, right? So let's take a look at that as well. So there are a couple of reasons why you would have an inspection performed in an area to begin with. And of course, that's responding to 311 complaints, as well as proactive neighborhood indexing, which I'll get to in a moment. And that kind of explains why we can see here there's a close relationship between the number of rodent sightings and the number of inspection failures which occur by zip code. Again, the correlation is not quite, isn't perfect by any stretch of the imagination, but you can definitely see just from a spatial perspective that these patterns are definitely overlapping. From just answering the question of inspection failures and how they occur, we can see that the most severe or the areas where rodent inspection failures are occurring the most often, again, are in northern Brooklyn, in this northern region of the borough, as well as the Bronx and the northern part of Manhattan in this other yellow region. Again, you can see this corner of northern Manhattan is highlighted again in yellow, but maybe not as much as you might expect compared to the rodent sightings which were observed before. Again, we can look at the rodent sightings relative to the number of inspections, and this indicates to us, so when we perform inspections, how many inspections are being performed for each rodent sighting that occurs. In the left graph, I show the ratio of inspections to rodent sightings that occur, and in the right graph, it's the ratio of rodent sightings to inspections. And all this indicates is like, how much are we inspecting a given zip code area for each rodent sighting that's occurring? In the left graph, we can see there's a couple of, it's again, this northern area of the Bronx, but a different part of the Bronx, more towards the east this time, which is experiencing far more inspections relative to the number of sightings or rodent sightings which are occurring. Additionally, you can see the same is true of this northern part of Brooklyn, although not all areas are captured by that pattern. Additionally, we can see the ratio of sightings to inspections, and surprisingly, you might expect these zip codes that are next to areas which are highly inspected to be of a similar pattern, but we see some deviance in terms of, the northeastern and northwestern parts of the Bronx specifically, these zip code level areas are experiencing far fewer inspections relative to the number of sightings which are occurring. Here, we're just simply providing a more explicit view of which areas are over and under inspected relative to the number of sightings. Any area that's highlighted in yellow, again, indicates that it's inspected at least once per every sighting, which occurs in the zip code level blocks. And any area highlighted in purple had more sightings relative to the number of inspections which were performed. And again, we can see from here that in the southern part of Brooklyn, as well as portions or four or so zip code level blocks of Staten Island, and then Queens as well, there are some significant patterns of areas where there are fewer inspections performed relative to the number of sightings which occur. And so how can we explain these differences in terms of where areas are receiving more inspections than sightings or fewer? And there are a couple of reasons for this, or a couple of potential reasons. The first one, again, as was mentioned briefly earlier, is that rodent inspections are performed on the basis of where 311 complaints are called in. This, of course, would indicate that you would expect a similar number, but in some cases there may be redundant complaints or higher frequencies of complaints, and the agency in question might perform a single inspection for several complaints, or there may be some overlap in in that area. In terms of explaining why some areas might receive more inspections than sightings which occur, we can turn to the neighborhood indexing program. This is another reason why the this is another reason for why inspections are performed in different areas according to nyc.gov. And these may not be triggered necessarily by rodent sightings, but they're used to try and get an understanding of the rodent issue or how infestations of rodents are building up in bigger areas. So when inspectors go into a particular zip code level block or a series of buildings, they may be investigating multiple areas at a single time. The last question you might ask about this is, okay, do we have underserved communities here? Is this because of potential discrimination in terms of, how we're applying inspection practices or so forth? And the data indicates that this isn't the case. Generally speaking, it seems from the data that median household incomes, which I'm using as a proxy for kind of the inequality, so to speak, across New York, indicates that the overlap between, median household incomes and the rates at which inspection sightings, or the ratio of inspection sightings to the ratio of rodent sightings to inspections doesn't correlate too well, which can be seen from these maps right here. On the left, we have a picture of the areas which are highlighted to indicate the areas where the median household income is the lowest, and the graph on the right indicates where the number of inspections performed for each sighting is the highest. And as you can see, the pattern actually overlaps to a certain extent in these areas, indicating that that this kind of reasoning doesn't necessarily apply in this case. So we've kind of compared the rodent sightings and inspections, but we can also look into the inspection counts and the rates at which they're performed on their own. We inspected this more thoroughly in the modeling and exploratory phase of our analysis, but you can see that the number of initial inspections that are performed by each zip code and the number of failures for initial inspections are highly correlated. There's almost a perfect match in terms of these two maps up above. But when we look at the initial inspection passing rate by zip code, we start to see that pattern of Queens having a much higher inspection failure rate than was visible from just the inspection counts alone. And this can all be seen along this kind of waterfront area in the map. Additionally, we can look at the compliance inspections to kind of get an idea for this, but these don't generate many significant patterns of interest. So we can move on to the conclusions and wrap this up. So at the end of the day, when we're trying to get insights from this data and trying to generalize information that we gather from the visualizations, we can come up with a couple of recommendations. For individuals and visitors who might be traveling in New York or walking around New York, the main goal is to try and avoid seeing rodents as much as possible. And so from that perspective, rodent sightings is a very good metric for trying to quantify how significant the rodent problem is. You want to avoid areas as much as possible where the number of rodent sightings is significantly higher than others. And for inspection agencies, the recommendations you might draw from this analysis are that it might be important to look at areas which are under-indexed or have fewer inspections relative to the number of sightings, or areas where we may be investing too many resources into inspecting areas that are already thoroughly investigated. And with that, I'm going to hand it back over to Professor Yan to wrap this up. Thank you very much.
Thank you, Josh. Well, thank you all the student presenters. I think we are open for questions. We have about 5 minutes. And we are very grateful for the New York Open Data and the team supporting the New York Open Data. And we know there are people from agencies that are relevant to rodent sighting, and we are eager to hear what they say. Okay. One question on methodological comments. Sample size is large, so many hypothesis tests will show significant difference. Yeah, exactly. When you have a big data, then any small tiny difference can be detected. So statistically difference does not mean practically there's a difference. Lack of fit for regression models also needs follow-up. Yes. Yes. Oliver has a question. I would also think about underserved communities in terms of who decides to call 311 when there are rats. And it could be interesting to compare to population adjusted usage of 311 overall by geography. Yes. Yes. So yes. So well, we don't know who decided to pick up the phone call to make the phone call. So the same rat, right? If the same rat appears in a highly populated area, and there's high chance the same rat got reported multiple times, and then that's something that can be further investigate. I think that's also why you have that in some zip code that you have that ratio. Right? There are much less inspections than sightings, a lot less.
Yeah, I think, the difference between indexing and complaint-based inspections is quite large in terms of the indexing inspections is more of a ground truth versus you have to layer when you think about complaint-based inspections. It's this layer of a human had to decide, I saw a rat, I should call 311. So it's a bit tough when those two types of inspections are sort of layered on top of each other in the data to disentangle that.
Oh, Oliver, do you know that whether we have information whether we can tell from the data set which inspection is? So
no, I put in the chat, there's a private version of the data I've looked at that has that called out, but the open data set does not have that yet. And I think it would be great if it was added as an additional data attribute. I think without that, there's probably some way to infer by the geography, because I think it's published where the indexing zones are, but that it might be imperfect, the kind of inferences you can make there.
Maybe one last question. What is causing more inspection failure in certain parts of the city?
I think based on the analysis that we did, at least my spatial analysis, I would say it's a difficult question to answer about which covariates specifically. I think Isabel did a good job of kind of discussing what covariates are relevant to inspection failures generally. We saw a negative correlation between, I think it was population. You can answer this question if you want to, because populate. Do you want to share on?
So running the binomial model, the covariates that had, first of all, the largest impact, I believe, were median household income and occupied housing units. And then those were both had a positive relationship with the passing inspections. And then the only two covariates that decreased the likelihood of passing inspections were population density and housing units. So the population density does make sense in context. There were some interesting ones, like the housing units, for example, that could be further investigated, because if you think about it logically, it seems a little counterintuitive. And there were a few like that with further investigation could turn up some interesting results, I would say.
Thank you so much, Professor, and everyone from UConn for your work at putting this session together. And thanks to all the attendees for joining us this afternoon.